My warm welcome to all of you to today's science colloquium. This is a joint venture between engineering, the college, CNSI, and medicine. Before I announce the speaker, I think I got to make some few more important announcements. One is that there is a reception after the seminar, so there will be some food. So you're all welcome to enjoy the food outside in the lobby. And the second is we are grateful for the support of Afric family for this colloquium. Now it's my great pleasure to introduce Greg Carman, who is a professor in the Mechanical and Aerospace Engineering Department in the Henry Samueli School of Engineering and Applied Science. And I would like to note there are two reasons why he was selected to be a speaker. And one of them is that I was chair of the recruitment committee that hired Greg. And the second you will know shortly. Greg received his PhD from Virginia Tech. He joined UCLA Engineering in 1992 as assistant professor. He became an associate professor in 1997 and full professor in 2001. Here at UCLA Engineering, Greg leads the Active Materials Laboratory, which explores the multi-physics behavior of active materials. This includes piezoelectric materials, which generate electricity when deformed, and magnetostrictive materials, which change shape with magnetism. His research in these areas earned him the Adaptive Structures and Material Systems Prize from the American Society of Mechanical Engineers in 2004. Beyond his lab and teaching duties, Greg has taken on two big leadership roles here at UCLA. And this is the second reason why I think Greg is a great selection for today's colloquium. He is an active and prolific collaborator across several disciplines with some of the great scholars here at UCLA. For several years, Greg has been the co-executive director of the Center for Advanced Surgical and Interventional Technology, or CASIT, based at the David Geffen School of Medicine. CASIT researchers have developed technologies in nano telemedicine, telesurgery, and robotic surgery. These new technologies have enabled doctors to perform surgeries previously thought impossible. More recently, Greg has led a very competitive center on new multidisciplinary engineering research, and that center's Engineering Research Center from National Science Foundation. I must mention that there were 103 applications, and NSF picked only 3, and Greg's was one of those. That's a remarkable achievement, and UCLA Engineering has gotten an ERC after a lapse of 30 years. Called TANMS, or Translational Applications of Nanoscale Multiferroic Systems, this new center aims to revolutionize consumer electronics through increased efficiency and reduced physical size. And achieving these goals is what Greg will talk about in today's presentation, titled Future Nanoscale Multiferroic Devices. Please join me in giving a warm welcome to Greg Carman.
Hopefully it is. Well, thank you so much. Hopefully you'll enjoy this presentation today. So I think VJ actually covered most of my overall slide here. So the one thing, look, what you're going to see today, really, I would like to believe, laid the foundation for the NSF ERC. The one thing I do want to point out, $35 million over 10 years. We're also teamed up with, there's a lot of professors here on UCLA campus participating in this. We also have Cornell, UC Berkeley, CSUN, and ETH Zurich, Switzerland. So we have an entire group of about 16 to 17 faculty. Also, as Vijay pointed out, I'm co-executive director of CASET. The only reason I want to bring that up, you're going to see some implications that the technologies we're developing may have some significant consequences in the medical side. So I'd like to believe that we're bringing along the medical community with us also. So let me just dive in. And the first comment is, all the research you're going to see today, really I didn't do. That the comment is I just drink coffee, and the people who do the work are really the students and the postdocs. And this is a picture of my group here. These are the names of the people who really contributed significantly that came from my group. Now, there's some of you in the audience who also contributed some of this work that is in this presentation. And as I get to that, I'll actually name those people by name when I get there. So look, I think the best thing to do in a presentation is sort of tell you where I'm going before I get there. So let me give you an outline. So first, I'm going to start with motivation. And the general motivation is electromagnetic devices, like the three you see up there, are fairly ubiquitous throughout our society. And of course, the goal of our society is maybe shrink them down smaller and smaller. And of course, you see some of the publications today about Apple creating a wristwatch with all of these neat, fancy features in them. And so this presentation along that line of thought is, can we compact all of this stuff into the size of a watch? Dick Tracy's watch, right? Some of you maybe have read that cartoon character before. And if you read it, what you'll see, some of the magnetism people always cite this quote that was in that fictional character that says, look, the nation that controls magnetism will control the universe. So really, the meat of today's presentation is about voltage control of magnetism. Now, maybe we can control the universe, maybe we cannot, but at least we can have a goal there, right? And really, I'm going to talk about film, microscale, nanoscale, and atomic level control of magnetism. Now, after that, we're going to start coming back to applications. I'm going to talk about two applications today. I'm not going to talk about the memory application that we're doing in TANMS. I'm going to talk about an antenna application where we have dramatically reduced the size of a conventional antenna. Then we're going to talk about some work we're doing on a nanoscale motor, which has a very high power density. And at the end, what I'd like to do is wrap that back up to something that I saw as a kid and start saying, well, maybe a watch is too big. Maybe we should actually be thinking smaller than a watch. So let's dive in here. So I've said electromagnetic devices are ubiquitous throughout our society. And we have to ask, well, how do electromagnetic devices presently work? So the argument is they work on a discovery made by Oersted some 200 years ago, where he discovered if you pass a current through a wire, you create a magnetic field. So we see a current going through the wire, and you create a magnetic field. This technology works fabulously well at the large scale. The problem with this technology, it doesn't scale with size. So the physicists, engineers have always known as we shrink down, this technology has a problem. And maybe in simple languages, let's articulate what that problem is. As you shrink a device down that has a wire in it, the diameter of the wire decreases. As the diameter of the wire decreases, so does the amount of current you can flow through that wire, which limits the amount of magnetic field you can create. Therefore, the energy density of electromagnetic devices typically does not scale with size. They typically start falling apart as you get to smaller and smaller scales. Now, if you say, well, what's a benchmark value? You'd like to say, well, if you had to look at a field, maybe the benchmark value is maybe you'd like to create something on the order of a kilooersted. Keep that in the back of your mind. And what are we doing under TANMS? What we'd like to do is basically use an intrinsic approach to control magnetism. What do I mean by intrinsic? It means let's apply an electric field or voltage and intrinsically control the magnetization state of a material. Maybe in simple languages, that's just taking a permanent magnet and being able to turn it on and off with just having a battery attached. Now, what's really cool about that idea is if you shrink it down, first of all, electric field does scale with size. So if you look at this, actually the energy density scales with size, so we can shrink it down to very small levels. So this approach, what we call it, is a multiferroic type of approach. Now, I didn't invent it. It's been around for quite some time. And if you look at this tetrahedron over here, really what it consists of is a piezoelectric. Well, let me take a step back. There are some materials out there which are single phase. which are able to convert energy from the ferroelectric phase to the ferromagnetic phase, thus multiferroic, directly. However, those are typically weakly coupled, so if you're looking at making devices, it'd be very hard-pressed to make a device. Now, there's composite approaches out there, and there's three types of composite approaches. One is sort of interphase type of effects using exchange-coupled phenomena. The other is charge-based phenomena. We're not going to talk about any of those today. What today we're going to be talking about is a composite-based phenomena where we're using a piezoelectric, where we transfer energy from electrical to mechanical, and then a magnetostrictive or a magnetoelastic material where we transfer energy from mechanical to magnetic. So we go around this outside portion of the tetrahedron. Now, why that's so nice, if you look at all those technologies for multiferroic I just talked about, you say which one actually today has the promise of transferring a lot of energy from one state to another, it's the composite strain-based approach which I just described. You may be asking how much can you actually transfer as far as energy? Optimistically, 60 to 80%. So this could be a very efficient system. If you look at this little cartoon down here, really what we're doing is we're just taking a piezoelectric, gluing it to a magnetostrictive so that we apply electric field, we can actually control those magnetic dipoles. So let's say you buy into that. The next question you should have for me, why do you want to do this at the nanoscale? Well, the next question you would like to ask me is, why would you like to do this at nanoscale? And look, I'm going to use VJ here as my partner in crime to sort of explain why this is important. So VJ understands magnetic materials, and if you have a magnetoelastic, which is a magnetostrictive material, the one comment you're going to make is it's a soft ferromagnetic material. You may say, well, what's soft? Go to your refrigerator. Now you put magnets on it, but the refrigerator isn't a permanent magnet. It's a soft ferromagnetic material. If you were able to go in with a little microscope and look at it, what you would see is a domain structure in there. And these domains would consist of north and south poles. And they would close upon themselves such that they contain the magnetic circuit. So if you're an outside observer like VJ is, you'd say, hey, that doesn't look like a magnetic material. I don't see any magnetic state. So now if you think about this, you go, well, wait, I read the literature. I can go back about 70 years ago, and some physicists discovered that if you start cutting up this refrigerator into smaller and smaller pieces, you get to a critical dimension that you get rid of domain walls. And lo and behold, you have a single domain structure. Now what's really nice about this, if you're an outside observer, you actually see the presence of a field. And you may ask, how big is that field? It's on the order of 1 kiloersted locally. So now we have a very strong magnetic field locally. Now the question is, can we control that with voltage or electric field? So the idea of TANMS is founded on is, look, we're going to take a ferromagnetic material, we're going to couple it with a ferroelectric material, and lo and behold, hopefully what we're going to do is, if you saw that going from north to south, we're going to actually manipulate that magnetic structure with an applied voltage at length scales on the order of 100 nanometers. Now look, I'm going to show you some PEM data that says, look, we've actually been able to achieve this. And then I'm going to show you some data on single domain structures that says, guys, we've actually been able to achieve this. So it's time to actually start transitioning this technology into potential devices. Now, whenever people give presentations, I always like to hear, because maybe I'm not involved in their particular area, how does their research fit into the grand scheme of things? So this picture is supposed to be about the grand scheme of things. Let's go back in time to maybe 1880. The Curie brothers discovered piezoelectricity, coupling between electric fields and mechanical loading. And then, do you know what happened is about 4 years later, Pierre Curie said, hey, do you know what? Since we discovered that, maybe there's this coupling between electric fields and magnetism. So he was one of the first people to have this idea about coupling phenomena. However, by the way, guys, he got it wrong, even though it was a great idea. Fast forward to 1960. The former Soviet Union, they discovered the first room temperature single-phase multiferroic. However, by the way, it was crappy. Now, you would never use it for anything. It was just sort of a novelty, a scientific curiosity. Fast forward to 1994, Schmidt actually coins this term multiferroic you saw on that first slide I put up there, TANMS in TANMS name. Now, what happened in 2002 was people at Penn State actually took magnetostrictive material bulk, glued it to piezoelectric material bulk, and lo and behold, all of a sudden, a revolution started. 1,000 paper plus have been published in the last decade. Once again, you should be asking, well, how does our research in TANMS fit into the grand scheme of things? So look at this bottom box down here. Let's now focus, because I tried to make this argument to you, nanoscale is important. So first, let's look at thin film multiferroics, where we're talking about strain-mediated phenomena. Only about 50 plus papers out there. Let's go down and try to control single domain elements. Only about 10 plus papers out there. And then let's even go down smaller than that. Let's go down to the superparamagnetic level. There's really only one paper out there, and that's really by the group here at UCLA. So let's now dive into some work. So enough motivation. Now let's talk a little bit about research. So what you're going to see first, let's talk about the structures. The first thing is we're going to focus on a PMNPT as our ferroelectric phase. It's single crystal. And you should be asking, well, why do you want PMNPT single crystal? Comment number one is all the structures we're talking about are nanoscale, so we need an extremely smooth surface. So I can get this with actually 1 nanometer roughness. The second thing is this PMNPT, I can actually get different cuts of it, so I can actually design in what strain state I get. That means I can have an isotropic strain, or I can have an anisotropic strain. And if you want to deal with magnetic anisotropy, that's a very critical component. Now, on the top surface, what we use nickel film. Is nickel the best magnetoelastic material? No. However, it's a sufficient magnetoelastic material. It was one of the first magnetoelastic materials ever to be used in sonar transducers. So it's good, it's not the best. So you may ask, well, why did we choose it? It was easy for us to fabricate without having to go through the headaches of making very exotic materials. Because once again, we want to get close to applications and actually just identify potential possibilities. So now that we have the structure, what we're going to do is put it together. We're going to apply an electric field, which is going to strain that thin film. And the next 3 slides you're going to see are only based on thin films at different dimensionalities. Now look, if you look at the thin film, what you're going to recognize is that you have domain states in those thin films. Now what's really important, if you look at that top surface, you'll see those north and south poles. So if you're an outside observer, if you get the right type of film, you can actually see that. And what I'm going to try to show you is that we can apply an electric field and actually have those to vanish. So once again, we're going to see some thin films where we see outside north and south poles, apply an electric field, and it's going to vanish. So let's go into some data now. We're going to start off, first film is going to be 35 nanometers thick. Now what's important about that thickness is all the magnetization states are now in plane. Did I discover that? No. That's well known in the community. So we chose a specific thickness of film. This is a plot of strain versus electric field for the ferroelectric that we're using, the PMNPT. This cut here is anisotropic strain. So what you see here is you'll see the X strain and the Y strain. So X is this direction, Y is this direction. So they're different in plane. Now that's very important. Now the other thing I want to point out is what magnitude strain are we looking at? Now some of you may not hear strain that often, so let's just talk about percentages. We're talking about 0.1% strain. Is that a big number? I'm going to argue that's really, really small. So we're not talking about these large percent strains that sometimes you see in the community. If you go fly an aircraft, you ask, well, how much strain was that aircraft designed to withstand? At least 0.5% strain. So if you put this on the aircraft, it's below that strain threshold. So now let's look at some data. So over here you have magnetic response of our thin film. That's just one film. But we're going to look at the response along the X direction and along the Y direction. Now you may not look at magnetic curves that much, but you'll notice there's a difference between those two curves. And what you see is as you take the magnetic field off here, you actually have a really high remnants, where over here you have virtually no remnants. So what you're supposed to take from this is down here you have an easy axis, up here you have a hard axis. Now what we're going to do is walk through and apply voltages. So first time we apply voltage and it shifts to blue. Notice both of these curves shift. If you heard the terms I said hard and easy, this curve now is suddenly becoming more easy. This curve is suddenly becoming more hard. We can apply a little bit larger electric field and a little bit larger electric field. And about 1.2 megavolts per meter, all of a sudden this red curve up here looks about like this red curve down here. And now we've actually reordered that magnetization state such that it's in plane isotropic. It doesn't matter what direction I go in. Finally, we go up to about 1.6 megavolts per meter. now we've actually reoriented the easy axis from the y direction to the x direction. So we've rotated it by 90 degrees, and these are through external measurements. Okay, so now you've bought that, hopefully, on 35 nanometer thick film. Now let's go to something slightly thicker, 60 nanometers. Let's don't look at magnetization curves. Let's look at MFM, magnetic force microscopy. And what we're going to do is we're going to take this tip and just scan it along the surface. And what we argue is that you'll see local south and north poles coming out of this film. And as this magnetic tip goes over it, it's going to create these stripe patterns. So you can imagine the black stripe is north, the white stripe is south. And the question is, can we control that? Now, by the way, this is entirely different phenomena than you saw in the preceding slide. Before, there was no out-of-plane domains. Now they're out-of-plane. Now let's go in and look at what we can do here. So we're going to look at an AFM image first, and down here is the MFM image. And this is at 0 megavolts per meter. Now let's apply a little bit higher electric field. We've applied 0.4 megavolts per meter. Notice down here, everything starts getting fainter, which means the strength of those north and south poles are suddenly start to vanish. Over here, when we get to 0.8 megavolts per meter, now they virtually all vanished. So now we've theoretically taken a structure which has north and south poles pointing out of the plane and actually distributed all to lying in plane, sort of like we had on that preceding slide. Now you say, well, what happens if you take the electric field off? Well, you go back to the original state. Yes, there are some pinning states here due to the domain formation in the ferroelectric. So this looks pretty cool now. If you can do that, let's go to thicker films, right? Why don't we just go to bulk? So now we go to 100 nanometers. Remember, went from 30 to 60 to 100. We still have the stripe domain patterns here. Outside observer can still see them. But now when we apply electric field, look down here. Virtually no change. Does that mean nothing's going on inside the material? Nope, things are going on. But as an outside observer, it's a soft ferromagnetic material, so you've just reoriented everything. So from an outside observer, it looks constant. So I'd like to say I've made the argument at this point, small is better for this type of technology. So if you buy that, let's now go in and start making things small. So because that was continuous film. So what we're going to do now is we're going to look at some geometries between 100 nanometers and about 5 microns. How big is 5 microns? That's about the size of a red blood cell. So what we're going to do here is we're going to use basically CNSI facilities. And I have to point out here, one thing I love about being here on UCLA campus is we really do have excellent facilities. Because a lot of the work you're going to see cannot be done at other universities because they don't have the same facilities we have here. And I think that's due to we have cross-cutting collaboration across not just departments, but also across schools. So today what we're going to look at is we're going to look at some shapes about 2 microns by 2 microns. Now, that's not real small. Then we're going to go down and we're going to look at a ring structure. This is about 300 nanometers if you can't see it. So we're getting smaller. And then we're going to go down to something about 100 nanometers in size. Now, I'm going to plant a seed. If you look at this, this may look like a motor to you. And over here, this should look like a bit of memory to you. So now let's go through and let's see what we can do. So we're going to start off with the 2 micron by 2 micron dot. Now that's not single domain yet. Now for this work, we had to collaborate with some people over in Germany. And it was Matthias Klaus at Johannes Gutenberg Institute. And we used photo emission electron microscopy to actually image the domain structures. So you see this picture down here? That's the 2 micron by 2 micron element. And as you shoot X-rays through, you know this white area here? What that means is your domain is parallel to your X-ray. You see this black region down here? That means your domain is actually perpendicular to your X-ray. Now you see these gray regions front and back? That means your domain is actually 90 degrees to your X-ray. So we have parallel, anti-parallel, and 90 degrees. So we have 4 domain structures in that 2 micron by 2 micron bit of information. Now, the other thing I need to point out, if you notice, we've drawn these arrows on these sides much larger than these. So this actually has an easy axis along this direction here. Let's go on and apply an electric field. So we step through with higher and higher and higher electric fields. If you watch this, hopefully you'll agree with me that white area is growing and that black area is growing. And suddenly you hit an electric field that virtually all of those 4 domains look equal intensity. Now this is called the Landau state. So everything is perfectly balanced in that structure. Now what we can do is we can go ahead and we can continue to apply larger and larger and larger electric fields. And all of a sudden when we get to this electric field over here on that nickel 2 micron by 2 micron element, what we see is we see domain structures which are prominent in this direction and less prominent in this direction. Compare the with electric field without. And what you should see there is here we had an easy direction going along this axis. Over here we had an easy direction at 90 degrees. So just like we saw with that thin film nickel, we're able to reorient the easy axis. So now we can start to get more and more comfortable with controlling local spin or domain states. Let's start doing something a little bit harder. Now really what's interesting about this, and this goes to collaboration, is I started coming up with the idea of working on ring structures because of a presentation at CNSI here a few years ago from a professor from MIT was talking about rings. And when I saw that, I said, no, that's sort of cool. But she was controlling the magnetic dipoles with a magnetic field. I said, well, why can't we do that with an electric field? And I gave it to one of my students, Josh Hockland. He went off and ran with it. And if you look at the structure, what's really nice about it is you can create an onion state embedded in that, where you have a north and a south pole. Now, the reason we like this ring structure is there's no shape anisotropy. So if you look at it, it's symmetric as you walk around the ring. So what that implies is that you should be able to have an easy time reorganizing those spin states. And that was our premise. So once again, we go in and we study this structure with MFM imaging, which once again is over here at CNSI. And what we do is we come up with our initial onion state. This is the north pole here. This is the south pole at 0 megavolts per meter. Now, all of a sudden, we apply an electric field, and lo and behold, we've rotated that by 90 degrees. And once again, I want to plant the seed. If you look at the structure, you go, wow, that just looks like a conventional electromagnetic motor. All you got to do is run that north and south pole around the ring, and now you have a motor. But now the motor's at 300 nanometers, not several centimeters. So this looks like some interesting stuff here, but let's go smaller than this. So as we tried to go smaller, we started finding out we can't just go through this make it and test it philosophy. We have to rely on analytical models. So I'm going to spend one slide just on analytical models real quick.
What about domains within the rings?
Right now, so the main walls depends on what size ring you actually fabricate. So you can fabricate a ring without any domain walls, depending on what your properties of your material are and what's the size of your ring. So you'll get to a size that you have domain walls, and you'll get to a size that you actually start forming vortex structures. Typically, we're focusing on ring structures below about 3 to 5 microns. So now we started coming up that we really had to start looking at analytical models. And the first model we looked at was a very simple Stoner-Wohlforth model. And that does well as far as sort of simple descriptions, but it doesn't really get you to actually design structures. And the problem is, if you start making things, that doesn't work. So the next thing is you can go over, and we came across this by working with Kang Wang up in electrical engineering. There's micromagnetic simulations. And look, the magnetics guys have been using these for quite some time. And it's very easy to code in magnetoelastic properties to that simulation. However, guys, there's one thing they're missing. So I'm a mechanical engineer. They're missing the mechanics. So once again, if you code this into your micromagnetics, depending on your structure, you're going to get it wrong because we got it wrong first also. Finally, we went to LLG plus mechanical equilibrium. Now what that means is our strain state isn't constant in that structure. It's really not constant. There's things like shear lag. So you have to take this in consideration. You say, well, how bad is it? Let's don't even worry about this. Let's just look at some data for LLG plus magnetoelastic. This is magnetization versus field. If you look at this breadth here, it's about 800 Oersteds between with strain and without strain. Now let's go to LLG plus equilibrium. The width between these curves are dramatically smaller, 200 to 300 Oersteds. So really what you should be thinking is, I can't use this, I need to use this. And the other thing is just how many people have done this today in the world? There's only a handful of people who've actually modeled this type of velocity. You say, why? Micromagnetics has been around for a long time. However, that community has actually tried to choose materials which are not magnetoelastic. So they said, we don't need equilibrium. Now, in this, you actually need coupled PDEs. And you say, well, how does that compare to test data? These actually correlate quite well. So now we can go in and we can actually start designing single bits of information. So what we did is we came in, and the goal here is we can fabricate things now. And we want to be able to apply an electric field such that all the spins in the single element, and once again, this is about 100 nanometers, actually rotate when we apply a voltage. So we go through and we do our simulation down here of LOG plus equilibrium. And lo and behold, yep, we can find a shape that will rotate when we apply that voltage. Now the problem is how do you actually visualize this? And this is where, once again, we had to go to Switzerland. Right now we're working with the colleagues up in Berkeley to do PEAM studies on an individual element. So this is some work on the PEAM facilities. Look at this circled region down here in red. You'll notice two dots. That corresponds to this element up here. And you'll notice they're white and black. And you'll notice this little green. Watch it when it goes 0, you have white and black. Remember what I told you about PEAM? If it's white, it's parallel. If it's black, it's anti-parallel. And if it's gray, what did I tell you? It's 90 degrees. So if you look at this little image here, let's wait till it gets to 0. As it starts walking up and it hits about 75, it suddenly goes gray. So we successfully reoriented those spin structures now by 90 degrees. I think this was the first demonstration of this. So you made it like that and said, well, let's go smaller than that. So we're at 100 nanometers now. Let's go down to a smaller size. Now, if you talk to physicists, they like this, and the memory people hate this. Because what happens as you get smaller and smaller, you reach something called a superparamagnetic element. Now, this is really cool, I thought. And when I first heard of this, is like you take a size, and we know we have single domain structures. As I start making it smaller and smaller and smaller, you get to a critical size that this is no longer stable. What happens, it starts just flopping around. Now, all the spins are cooperating together, but at any moment in time, they're pointing in a different direction. So if you were to average that over a very small, finite amount of time, you'd say there is no magnetization state here. So when I heard that, I said, well, you know, I think what we can do is we can actually pop back and forth between these states by just stabilizing it with more energy. So all we have to do is put anisotropy in there, and we can pop from superparamagnetic to single domain. So I gave the student the problem. He went off, and after a year, he couldn't make small enough particles. And how small are we? We're no longer 100 nanometers. We're trying to get down to about 10 nanometers now. So we're approaching the size of an atom. And what we found is he had a hard time fabricating. So I was talking to Sarah Tolbert over in chemistry. She goes, oh, that's easy. We can do that. And Laura sitting in there in the audience says, oh, I can do this. I think after a couple of weeks using thermal decomposition, she was able to make these nickel nanocrystals. How big? About 10 nanometers. Her working with Hyung Suk were able to put those down on our PMNPT surface. This is a monolayer here. And then they capped it with platinum. Why did they cap it with platinum? Is to have good strain transfer between the ferroelectric and the magnetoelastic material. Well, now let's look at some data. So this is the sample without an electric field. And we measured the magnetic states along two directions. One is the X and one is the Y. So here's the X and here's the Y. Notice they look almost identical. Very little hysteresis, so the argument is that is superparamagnetic at room temperature. Now let's take that same sample but apply an electric field to it. Not change the temperature, and let's look at the MH curves again. So by the way, this is an anisotropic cut, so you actually have a large compressive strain in this direction. The other thing is nickel is negative magnetostrictive. So if you compress it, the domain should align with that compressive strain. Lo and behold, we got something that looks single domain. The y-axis is the easy axis. The black axis of the X is the hard axis. So now we can theoretically pop between superparamagnetic and single domain at one temperature. Now if you're a physicist out there, you go, well, look, I don't like those MH curves. A better way to measure really superparamagnetic behavior is blocking temperature measurements. So let's go in and quickly look at zero field cooling curves. And you may ask, what's a zero field cooling curve? That's where you're measuring the magnetic moment. You take the system, you cool it down to cryogenic right around 0 degree Kelvin. Then you apply a very small magnetic field, and you watch how the magnetization state changes as you increase temperature. And you'll get to a point where it maximizes, so the spins are aligned, and then above that point, it's super paramagnetic. We call that the blocking temperature. This measurement was done on the as fabricated particles on the PMMPT substrate. Now down here is that same sample, same measurement, but now we applied an electric field. Now what you'll notice is up here TB is around 300, down here TB is around 340. So we shifted the blocking temperature by about 40 degrees Kelvin. Or another way I like to put it, at room temperature we have super paramagnetic behavior. If we apply an electric field, we can actually stabilize that and have single domain. Now the one question some people ask me is, well, can you shift it more than 40 degrees Kelvin? Yes, we can. Why? I told you in the beginning, nickel is not the best magnetoelastic material. If you choose other materials like terphenol D, you should be able to increase that shift in blocking temperatures from 40 degree Kelvin to something like a couple hundred degree Kelvin. And you may ask, how close was this to an analytical prediction? Our analytical prediction said it should shift about 46, and we measured about a 40. So we think we're very much in the ballpark at that point. So at this point, I'd like to say I've tried to convince you we can control magnetic dipoles with electric fields. Now the question, is that useful? So let's go into... Sure.
Before you go on, the hysteretic behavior that you saw, was that predicted also through your modeling?
So right now in the model, it was just a balance of energy. If I take the properties that we know and the... so if I take the properties we know at that temperature and put in the magnetoelastic energy, I can come up with that hysteresis. But now, that's nothing new to people who do micromagnetics. So if you look at people who do micromagnetics, they go, yeah, we know you'll fall into this energy well over here, and there will be a large hysteresis if you pop out of that energy well. Now, the thing we don't do is we don't introduce into our micromagnetic simulation a temperature dependence. So what we have to do is we take one temperature and we know the material properties. We can predict those. We can go to a different temperature, take the material properties, and we can predict those using micromagnetics. Now, if you want to get into fundamentals, you can actually start using codes like LLB, which are a little bit more sophisticated, that bring in temperature influences. We have not done that in our group. And the reason we haven't is we don't feel right now to getting to a device platform, it's sufficiently needed. If you understand fundamental physics, I think you have to go down that route. So now let's go back to devices and applications. Now I'd like to say this is where you can start hooking the community. It says, look, there's some really important applications. Now I'm not going to talk so much about memory devices because I'd like to argue to you that everything you've seen about that single bit of information looks like reading and writing a bit of information. So we have a new approach to write a bit of information. So what we'd like to do is maybe focus in on the antenna and the motor, and once again maybe try to put it into a little wristwatch there. I'm going to show you results that we have now, I think, on the first multiferroic antenna. And so as a spoiler alert, I'm going to try to tell you that we've decreased the size of an antenna by a factor of 1,000. Now that's not small, that's really, really big. And I'm going to try to describe to you how we did that. The second thing there is we haven't made this motor yet. This is just an illustrative example, but we think we're very close to getting to make that motor. Once again, if you look at the power densities of that motor, we think they're going to be larger than the power densities of the motors you have at the macro scale. Once again, truly a game changer. And finally, after I get done talking about those two, I'm going to come back and try to convince you maybe we can actually build a fantastic void ship, something I loved as a kid. So let's talk about antennas for a second here. To understand antennas, first you have to understand the basics. So I'm not going to go over Maxwell's equations, but hopefully you all understand antenna community uses Maxwell's equations. And if you had an antenna over here, you say, well, what's the physical dimension of the antenna controlled by? Most of them are resonant-based structures. So typically they're designed right around the wavelength. You may ask, well, what's the wavelength? The wavelength is nothing more than the speed of that EM wave divided by the frequency. And the speed of the EM wave is the speed of light. So really we have a simple equation to sort of get a rule of thumb of how big that antenna should be. Now remember I told you in multiferroics we just don't have electromagnetic energy, but we've got mechanical energy. So if you're a mechanics guy, you go, hey, I know the speed of light is really, really big, but you know what? The speed of sound is really, really slow. So if you start looking at this equation, you start going, well, maybe there's something to be done there. No, I was working once again with Kang Wang up in electrical engineering, and he was working on a spin wave bus with us, and he was trying to propagate a spin wave. And I was really always fascinated. Spin waves, which have EM components in it, they only move about the speed of sound. I was thinking, boy, maybe we can try to take something like this, where we had a multiferroic transmitter and a multiferroic receiver, and actually make an antenna that would be useful maybe for your iPhone. And you say, well, what type of impact might that have? Let's just look at some basic numbers. Remember, this length of the antenna is related to the wavelength. So if we look at 100 megahertz, lambda for an EM wave is on the order of 3 meters. However, if I can transition that to sound, all of a sudden it's 30 microns, really, really small. Well, let's say your cell phone operates about 2 gigahertz. Lambda is about 15 centimeters. Hey, if I can transmit that to sound, 1.5 microns. I know you had this iPhone problem at one time. Maybe if you had this, you'd never had that iPhone problem. Now the question is, how can you actually transfer that energy between electromagnetic to mechanical? And I'd like to describe it in a very simple process. So what we have here is we have an EM wave coming in, and let's just say it's 500 megahertz. Very long wavelength, about a half a meter. And what we're going to do is we're going to put some nickel elements down. And what we're going to do is, as this EM wave impinges, remember there's a magnetic component in it, they're just going to vibrate, just like a magnetostricted material. And what we're going to argue to you is that now we can actually cause a mechanical resonance. And of course, the mechanical resonance is in this piezoelectric material. I can propagate that wave, and if I put electrodes over here, all of a sudden I can actually read out a voltage. Hey, I've got an antenna design. What's really nice is we went from 0.6 meter down to maybe 6 microns. And of course, the question you should be asking is, are those frequencies realistic for sound wave? Oh, lo and behold, you go out and you can find papers. Yeah, you can go up to gigahertz. Not a problem one bit. So now all of a sudden you go, boy, this might sound interesting. Can you actually build something to do a proof of concept on this? And we think we've done that. So the first thing we did, we said, well, let's just use back of the envelope calculations. So I know about what sizes my nickel structure should be. I know I've got to put electrodes here. We sort of knew what the electrode spacing should be. And let's just go in and build this thing, such that we have an EM wave coming in here. It'll excite these nickel magnetoelastic structures, which will create a wave, which we can then actually monitor. Well, Paul went out and fabricated this. Once again, just back of the envelope calculation, said, let's go run and test this. So we went and ran and tested it. So we went up to Ethan Wang's lab up in electrical engineering. We had an antenna to actually broadcast the EM wave. We had our little sample here. We could apply H-bias, and this was our little sample. And lo and behold, this is the results. This is S12, which in simple words means the output we're receiving from our antenna versus the input coming from this antenna as a function of frequency. And let's say 500 megahertz is right in this region here. We have two curves here. Red is the control. And why do we have a control? Because we have electrodes down. The EM waves are going everywhere. Maybe we're just getting garbage. So that's really our antenna without any nickel on it. Then we have our actual specimen down here. We looked at this for a long, long time. We kept convincing ourselves, we see something, we see something. It was just garbage, guys. And then, talking to Scott, and this was done with collaborative work in Boeing, they said, the only way to do this problem is you really have to do modeling. So we bit the bullet, and Scott went off and tried to model this. And this is truly multiphysics at this point. The first thing he had to do is he had to model the EM wave coming in to the structure. So that's just Maxwell's equation. Once he modeled that, the interaction with the substrate, he knows what the magnetic variation spatially in that nickel element is. So then he created another model, fed these results into this model. Here you have mechanics, magnetostrictive, and piezoelectric. And then you can start exciting this to see what's going on. But we could only build a finite size model because we started running out of time and space. From this, we got displacements and voltages, which we fed into another model, which actually allowed things to propagate. And on the surface, lo and behold, we were able to get voltage output. So that's the multiphysics model, now the good, the bad, and ugly. Well, the good is look, things work really well, but you know what? It took us a lot of bad to get there. This wasn't an easy problem. He had to go through a lot of iterations to really fundamentally understand what's going on. So it wasn't like eureka, it's there. The ugly was really that first sample I showed you. No reason to even show you. It's too ugly to even talk about. So really, with these type of designs, you can't just use it to make it and test it philosophy. You really have to do modeling. So let's go in and let's now design a new antenna using our models. Let's go in and build this antenna, and let's look at what the results look like. So once again, we have our system up here, the same output, S12 versus frequency. The blue is our material response. The red is control. Now, if you look at that, I'd like to argue that's a really clear, distinct signal. So this is the first time, to my knowledge, that a multiferroic has actually been used as a receiver. Now, if you bought that, what's really important here is it the best antenna ever? I don't know. Are there improvements that can be made? Most substantially. This is only the 4th generation. Remember, the antennas we have today have taken decades and decades to perfect. But what's really important is this line here. This antenna is 1,000 times smaller than a conventional antenna designed to receive at this wavelength. And you say, well, how big is that? Well, if you just take your finger, that's like taking your finger and shrinking it down to the size of a hair. So we've decreased it dramatically. So if you start really thinking about nanotechnology and nano antennas, this may be the direction to go in. So now let's move off to the motors, and then I'll start wrapping up. So on motors, the first thing is if you look at conventional motors, they're electromagnetic. Let's just start off with that and say, look, you have north and south poles here. Inside are your current windings, and that's how you turn on and off the magnetic field. And if you say, well, what's the power density of big motors? It's about 1 megawatt per cubic meter. Now, what's really interesting, if you look at this plot over here, this is power density versus motor volume. And notice these are both log-log plots. So it's very important. These aren't linear scales. So even though you start off with bulk motors at 1 megawatt per cubic meter, as you go down in size and you approach that, let's say, 1 micron dimension, all of a sudden it goes down to about 1 watt per cubic meter. So you went from 1 megawatt to 1 watt in the small scale. So let's just do justice and let's say what other research is out there. There is research on molecular motors. So molecular motors, yes, you might be able to get up to gigawatts per cubic meter. They use ATP. Look, it's a challenging engineering problem. The reason engineers like this is, do you know what? I can put that on my airplane because I can design for it. I can put that in my car window because I can design for it. And I can even put it in little toys because, once again, I can design for it. A lot of molecular motors, it starts causing a little bit more of a headache to try to get it into an engineering design. So my argument to you is if we can get this in the small scale, it's probably what we want from an engineering perspective. So let's now talk about our multiferroic devices here. And we put it up here in this green space. Now, if you notice, that's a big number. It's 1 gigawatt per cubic meter again, and you should be asking, how in the heck is that possible? Well, first of all, let's look at what limits this power density in the large scale. Because, look, we have the same material in the small scale that we have in the large scale. So energy density between those two, let's just say, are the same. So it's all that dictates power at that point is what operational frequency you can actually operate the electromagnetic motor. In the large scale, you're talking about 100, maybe 1,000 hertz. Now, when you go down in the small scale, remember that little ring I showed you? People have shown over in Germany that you can propagate that at 1 megahertz. So it can run around the ring at 1 megahertz. 1 megahertz times that energy density gives you a very, very large number. Now remember, right now, what do we have available to us? In this scale, 1 watt per cubic meter. Now we're talking about something that may be as large as 1 gigawatt per cubic meter. A truly revolutionary advancement if we can get it to work. So where are we on this? Of course, yeah, we can draw pretty pictures, but how far have we made it? So you've already seen the ring state here. This is the onion shape. So we have a north pole here and a south pole here. What we do is we just put electrodes every 60 degrees. And it's a really simple process. We apply a stress with the electrodes. Now we just apply voltage, and we're able to clock this 60 degrees. Then by applying a different electric field over here, we're able to clock this another 60 degrees. And finally, applying another electric field, we're able to clock at 180 degrees. So now I can position that magnetic dipole any place I want around the ring. So what I can do is I can just have it run around the ring at very high frequencies and actually very high power densities. So the question is, what have we done so far? Well, we've made the rings. You've already seen that we can clock them 90 degrees. We've went ahead and done the simulations that says, yep, this is possible that we can clock it around. And we've designed a structure. And the structure looks something like this. So right inside that middle portion there is the little ring structure. All the math says, look, this will work. And the problem we're having right now is we're not applying the right electric fields and we don't have the right electrode displacement. So we're relying on Chris Lynch over there to actually give us those placements of the electrodes and the size. And as soon as we have that, we're off and running with a very high powerful motor. So that's where we're on in the motor. And by the way, this is just some PEAM studies done over in Switzerland that says, yes, you can really look at the local magnetic state and you can change that with applied electric field. So now let's talk about science fiction or reality. So now I'm a member of CAS, and Mac Holmes had me one day. He introduced me to David Hopta over in the medical side. And David wanted to put in some really small sensors in these small diameter vessels to monitor traumatic brain injury, about 3 microns. And you saw some of the things that I presented today, and my mind started thinking, it's like, look, I know I've worked with catheters before, and the smallest catheters out there is about a half a millimeter. Can we make things small enough to put it in there that we can get close and just let it go? And of course, this movie, Fantastic Voyage, that I loved when I was a kid. And of course, we're not going to try to shrink people down, but can we build things of that size? And I'd like to argue, too, that it's possible. And if you look at the key features in there is A, you need a motor. And I think we're very close to having the motor. B, you need a transmitter. We have actually a transmitter right now. We just have to perfect it for this size. And of course, maybe you need some memory elements there. And what's really nice about this is now there's this huge project potentially coming out of the White House now on brain mapping. It has a lot of money focused, I heard, on the order of billions of dollars per year. And the question is can we use this technology to actually start mapping certain components of the brain? And I'd like to argue that it's possible. And all it does, it takes collaboration. So with that, I'm just going to try to summarize here what I've tried to cover. First of all, I try to leave with you today that multiferroics is a unique process to electrically control magnetization and really overcome Oersted's limitations in the small scale. The second is I'd like to believe I convince you we're able now to really reliably control magnetic states from 10 nanometers up to 5 microns and have fairly significant changes in that local magnetic field. Now, as far as devices, we've just started going down that route. I didn't show you the memory, but we believe orders of magnitude improvements of efficiency in writing memory. Now, all of you have a cell phone, you know it gets hot, and you start downloading and writing data. If you can reduce that heat generation, you've actually saved a lot of battery life. I'd like to believe I've tried to convince you you have the ability to make electrically small antennas now. And finally, this power output from this motor may be extremely large. Now, coming back to this Dick Tracy character, the nation that controls the magnetism will control the universe. Well, we think maybe that's not true, but we think the nation that controls magnetism in the small scale will have a significant impact on their economy and the future of this world going forward. And the thing that we try to convince NSF was when we got this ERC is ideas like this only come around once in a century. And we think now may be one of those times to actually cause a paradigm shift in how we control, design, and generate electromagnetic devices in the small scale. So with that, I just will say I'll take any questions, and thank you. The only comment I'll make is all the tough questions I'll pass on to my students. Thank you.